Alright, CNT125, Chapter 12, last little chunk of WAN technologies, wireless. So let's take a look at cellular to start. Cellular was initially designed for analog phone, and this was really in the 70s. But after the introduction, it didn't take long to want to try to start putting data across the cellular network. And today, probably substantially more data moves across the cellular network than voice traffic. But if we go back in time, here's some different generations of cell technology. First generation, or Gen 1, analog, and this was in the 70s and the 80s. Second generation, we actually could start doing digital transmissions up to 240K, and this was in your 1990s. Third generation, data rates up to 384K. This is now data communication using packet switching, not voice yet, but just data was using packet switching. This is in the early 2000s. 4G, this is pretty much where most things are living right now. Most of our cells and devices and so forth are 4G. Now we have all IP. All of the data and voice is now IP based. This was released in 2008, so roughly 10 years ago. Packet switch network for data and voice, yep. Throughputs of 100 meg for fast moving clients or gig for slow moving clients, up to a gig for slow moving clients. 5G is still in the works. You're hearing hints of advertisement of 5G devices, 5G networks, and they're expecting downloads in the neighborhoods of 20 gig, uploads somewhere in the neighborhood of 10 gig. That's kind of the expectation of 5G network or 5G devices. Cellular networks use one of two competing voice technologies, GSM or Tdma. So let's take a look at those. GSM, Global System for Mobile Communications, open standard, accepted and used worldwide. This one, the data is separated by time slots on channels using Tdma. Tdma, time division multiple access, is very similar to the time division multiplexing that T1 used, using time slots for the different users or the different phone calls kind of deal. TDM signals all come from the same source, such as a router. Meanwhile, your TDMA signals, multiplex TDMA signals, come from several sources, several different users, several different smartphones in the vicinity. That's a little bit difference there. This was first introduced with the release of 2G devices. And again, the idea is these different cell phones can get multiplexed together on one physical link, if you will, one physical channel, and the 24 simultaneous phone calls in the area can get multiplexed together into these little time slots. Here's a little time slot for your phone call, a time slot for your phone call, a time slot for your call, and then rotates back around and does it again. Initially only voice, but added data with evolution of GPRS, General Packet Radio Services, and eGPRS, Enhanced General Packet Radio Services, also called EDGE, Enhanced Data Rates for GSM. So some of you recognized EDGE in there. GSM required and requires use of a SIM card. The little microchip that goes into your phone actually holds data about the subscription, the subscription the user has with a cellular carrier. So if I'm going to connect to a Verizon network, I would need a Verizon SIM card, etc., etc. Okay. Meanwhile, CDMA, code division multiple access, spreads the signal across the whole bandwidth, wide bandwidth. Multiple users occupy the same channel, called spread spectrum. Codes on the packets keep the various cell calls separated. So a code on mine keeps it separated from a code on yours, so it knows whose is whose. CDMA networks do not require SIM card. Devices are compared against a whitelist, basically a database of subscribers and what their capabilities are. Some CDMA networks still use SIM cards for LTE, long-term evolution features, so it's kind of a some do, some don't kind of thing. Your network infrastructure for cellular. The cells are serviced by an antenna and a base station. The controller assigns mobile clients frequencies that they're going to use. And if I have to look at a map, I end up seeing cells depicted as a honeycomb here. And these towers on three sides basically create this cell. I think they're trying to show that here. The tower here, tower here, tower here basically creates this cell structure here. Anything in that cell would be serviced by those 3 towers. The cell sizes can range anywhere from 1,000 feet to 12 miles in diameter, but it's going to depend on your access method, the region's topology, population, amount of traffic, that sort of thing. So example, a high population, high traffic area might only have a 2,000 foot diameter cell with towers mounted on tall buildings. Meanwhile, a rural area with sparse population, towers might be mounted on hilltops or hills kind of thing, and the cell might actually span 10 miles. So it's all based on the population and the terrain and the volume of use in that area. Each base station connects back to the MSC, Mobile Switching Center, also called MTSO, Mobile Telecommunications Switching Office. You might hear one of those 2 terms. Each base station is connected to your Mobile Switching Center, either by a wireless or fiber optic link. The equipment at your Mobile Switching Center manages the clients, monitors their location usage patterns, switches cellular calls, assigns each mobile client an IP address, and that IP address, if you're dealing with 4G, that client IP address remains the same from cell to cell to cell and from one carrier's territory to another. Kind of hands that off, so that way there's some consistency there. Cellular technology is frequently used for data networking is your high-speed packet access plus. This was 3G technology released in 2008, and it's going to use MIMO. That should sound familiar as we start dealing with your upper standards of 802.11 wireless networks. MIMO, multiple input, multiple output, and some sophisticated encoding. Max of 168 meg downlink, 22 meg uplink. Uses these limited channels more efficiently and incorporates more antennas and MIMO transmission. Faster, more flexible technologies like LTE have overtaken HSPA, your high-speed packet access. So LTE, this is probably the most common. Again, most of us are probably living in 4G right now, using LTE for your data. So your 4G technology, different access than your HSPA. Theoretically can achieve downlink of up to gigabit and uplink of 100 meg, but they do vary and sometimes significantly less depending on distance and number of people on a particular tower. But currently the fastest wireless broadband service available in the US for your devices, your LTE. So last wireless technology is our satellite technology. With satellite, we're typically dealing with geosynchronous orbit satellites. So most of our satellites are circling the Earth about 22,000 miles above the equator in what's called a geosynchronous orbit. A geosynchronous orbit is when a satellite orbits the Earth at the same rate the Earth turns. So if it's orbiting the Earth at the same rate that the Earth's turning, it always appears to be stationary above the Earth, above the equator, if you will. Well, that becomes really useful because if it's always in the same spot up there, I can actually send a signal to it, use it to relay a signal to another continent or halfway around the world, if you will. And this becomes very common because you can use that point for communicating from A to B. And here's just an example of your geostationary orbit. There's low orbits, there's high elliptical orbits, but the geostationary orbit, it's basically orbiting the Earth is the same rate that the Earth is turning, if you will. Generally used to relay information from one point on Earth to another. I always like to pick on the Olympics. The Olympics are oftentimes halfway around the world. A lot of times what is happening is the signal is literally hitting that satellite and bouncing over to the Olympics over in Russia or halfway around the world, if you will. Your uplink signal from your Earth-based transmitter. Info is scrambled, signals encoded before transmission to prevent unauthorized interception. At the satellite, a transponder receives that uplink signal, turns around, and retransmits it to an Earth-based receiver in the downlink. Side note, your satellite contains typically 24 to 32 transponders. Each satellite uses a unique frequency for its downlink, and all these frequencies and orbits and so forth are assigned and regulated by places like ITU as well as FCC. And then the downlink signal coming from the satellite is picked up by a dish-shaped antenna. And those become fairly common because you're used to seeing dish-shaped antennas now. And I picked on this as just a television example. Here would be a satellite uplink truck. I picked on these guys because they're local, Pennsylvania Cable Network. Here's the satellite uplink truck. There's your satellite dish. They would actually aim that at a satellite, and the satellite can repeat that to customers like so, kind of thing. I'm just trying to give you a sample so you can see. Your geosatellites, type used most often by satellite data services, absolutely. Technology is well established, yep. Stationary receiving dishes on Earth can be counted on to receive satellite signals reliably. The only catch on this is weather permitting. You have rainy, foggy days that can actually inhibit your data signal. Okay. It's used to deliver television, radio signals, yep. Voice and video, yep. Think of the Olympics. Cellular and paging services, yep. Data service to mobile clients, remote locations, yep. You can actually have a satellite phone. You can actually use a satellite phone. Here's the different frequency bands for satellite communication. Different technologies might use different frequency bands. That's why they're listing them all for you. With each band, frequencies used for uplink and downlink transmissions differ as well. So you might have a 12 gig down or 12.1 gig down and 12.2 gig uplink kind of thing. Just as an example. Satellite internet services. Subscriber uses a small satellite dish antenna for the receiver. Exchanges signals with the provider network. Typical asymmetric communication. Bandwidth is shared among multiple subscribers. And sometimes the uplink is actually handled by a different device, like a DSL kind of thing. Throughput's controlled by your service provider, and it's slower and more latency than other options out there, yes. But if you're dealing with very remote connection where you don't have other services, this would actually work. And here shows, kind of example of moving data through satellite network. Also reminding here, dish satellite TV, that's receiving television signals from a known satellite above the Earth. Also, satellite radio falls in that category too. I can receive radio data from a satellite, so forth. There you go. There's the end of Chapter 12.